Another kind of emission that you have to consider is the emission that comes from dust grains. So we have dust grains in the interstellar medium, and they're mostly made up of graphites and silicates. These dust grains have a grain size distribution where you tend to have more small grains and much fewer large grains. This dust tends to be preferentially distributed in the molecular clouds of H2 gas. And that's because the conditions here are cool enough so that this graphite and silicates are not condensed by very high temperatures. So in a molecular cloud, you typically have a ratio of the mass of the dust particles to the mass of the H2 particles as being around roughly 0.01. So roughly 1% of the mass is associated with dust. And this can be problematic for optical astronomers, unfortunately, because where the most massive stars form tends to be in the most massive molecular clouds, and these tend to have the most dust. Unfortunately for optical astronomers, most optical and UV wavelengths are unfortunately absorbed by these dust grains. So if you have a young star which is emitting near UV and optical emission, then that emission is completely absorbed by an intervening dust grain. So if you have a cool dust grain like this, then the cloud becomes completely opaque and you're not able to see inside the cloud at optical wavelengths to see this young star as it switches on. However, there is a bit of a saving grace here in that this UV radiation acts to heat up this cold dust grain so that the cold dust grain now becomes a hotter dust grain. And this hot dust grain then emits like a grey body. So it emits thermal emission, which is then at far infrared wavelengths or infrared wavelengths. So from this, what you can say is that the far infrared radiation is a very good way to probe star formation for very massive stars where they're very much obscured by the dust in the intervening clouds. And you can see dust even in our own Milky Way at night, where you can see those dark bands against the sky, which is where these dust grains are absorbing stellar light. So the far infrared is actually a very good probe of the star formation rate of very massive stars. And as we've said before, the star formation rate of very massive stars is also very much the current and most recent star formation rate. And it's very good probe of what we call the obscured star formation rate. There is a very curious relationship between the far infrared luminosity from these dust grains and the radioluminosity from a normal galaxy. And if we plot the far infrared here on this bottom axis versus the luminosity at 1.4 gigahertz, what we get is a very, very tight correlation. And this correlation is called the far infrared radio correlation. Now, the far infrared radio correlation is perhaps a little bit unexpected, because in fact, at 1.4 gigahertz, only around 10% of the emission that we see comes from free emission. Most of the emission that we see is actually this diffuse synchrotron emission, where most of that is associated with these diffuse cosmic rays electrons.